Chapter number 8, Maxwell Equation. In this chapter, the main concern is what is the need of the Ampere's law to get modified, how Maxwell modified or redesigned the Ampere's law, and the concept of magnetic charges, and the Maxwell equation in the material and the boundary condition based on the Maxwell equation. Faraday law. Let us introduce the concept of electromotive force. Now consider a battery with a bulb as shown in the figure. The current is same all over the line segment around the loop at any given instance of time. During the first split of second after the switch is closed, the current is not same all the line segment around the loop. That shows the charge is accumulating, not flowing. The electric field due to these accumulating charges is in opposite direction of the current flow. That is, they are opposed the current flow. The effect of the mechanism is determined by the closed line integration of electric field. Therefore, closed path integration electric field E dot dl is equal to the electromotive force EMF. Now consider a wire. The same concept is studied when you keep wire in a uniform magnetic field. Now consider a magnetic field beam. These are going into the pitch. Okay, direction is into the pitch, and you are keeping up a loop of wire, and you are pulling that wire away in this direction, away from the magnetic field. Now consider moving wire with the velocity v through a uniformly magnetic field B pointing into the page. The charge in the line segment AB will experience a magnetic field. I have not connected any source of electric field into the loop. Loop is closed, but it does not have any electric source. But still, the line segment AB will experience a magnetic force. Now, those vertical component is q times velocity v. Drive the current around the loop in a clockwise direction. The EMF is equal to integration over a closed loop Fm, force of magnetic field, is equal to v dot bh, where h is the height and v is the velocity and b is the magnetic field. Although the magnetic field is responsible for the EMF, but it does not work. Then who work? The work is being done by the force of pulling. Okay. Magnetic field never perform the work. Then the pulling force on the wire perform the work. The integration for a path of force pulling is equal to velocity v bh, which is equal to EMF, electromotive force EMF. Now let's suppose phi m is the magnetic flux due to the magnetic field B. Therefore, phi m is equal to integration v dot dA. Now this dA is the area, so we can write h times x. Now taking the derivative with respect to time of above equation, therefore d by dt of phi m is equal to dh dx by dt. Now this dx by dt is minus of vt. Since b and v both are in opposite, velocity is in this direction, movement is in this direction, and the magnetic field effect is in this direction. Therefore, the minus sign account for the fact that dx by dt is negative. And this shows that the EMF generated in the loop is minus rate of change of magnetic flux for the loop. Therefore, EMF is equal to minus rate of change of electric flux, which is equal to BHV. Now, equation 1.8.11 that is integration over closed path E dot dl is equal to phi 8 and 8.12, that is electromotive force is equal to minus rate of change of flux phi m. If we equate both the equation, what we will get, phi m is nothing but integration of magnetic field over the area. If we substitute that in place of phi m, if circuit is rigidly stationary, then the time derivative taken inside the integration where it become a partial derivative, and therefore integration over closed path E dot dl is equal to integration deba b by deba t of dA. If we apply the Stock theorem on left hand side, therefore left hand side becomes integration del cross E dot dA is equal to minus integration deba by deba b respect to time deba t dA, and if we cut the surface integration on both the side, we will remains with del cross is equal to minus deba b by deba t. Now this is the Faraday law. Del cross E is 0 for static electric field, whereas in a moving electric field, the Faraday laws will be applicable. That is the main difference between, if you study ahead and you say that I have learned that del cross E is equal to 0. Yes, del cross E is equal to 0, but in a static electric field. When the electric field is moving, the Faraday law will be applicable. The negative sign in a Faraday law indicates the direction of induced EMF such as to oppose the change that produced. Now, electrodynamic equations before the Maxwell. We will remind some of the equations which we have studied. Gauss law, what we have studied, del dot E is equal to rho by epsilon naught. Faraday law, which we have concluded, del cross is equal to minus of deba b by deba t. Del dot b is equal to 0. Del cross b is equal to mu naught j. This is what we have Ampere's law. Ampere's law. These equations represent the electromagnetic theories before the Maxwell. Let's suppose we will find the del dot del cross E. As we know, the divergence of a curl vector is always 0. Now, we will try to find whether it is 0 or not. Del dot del cross E. Del cross E is nothing but minus of deba b by deba t. Now, if we take del dot inside, the minus deba by deba t is del dot b. Now, del dot b, as we know, is nothing but 0. Therefore, left hand side becomes 0 due to the divergence of a curl is always 0, and the right hand side is equal to 0 due to the del dot b equal to 0. That means it holds good. What about del cross b? Now what we know, del cross b by Ampere's law is mu naught j. Now mu naught j, mu naught will be taken outside, is del dot j. Now left hand side is, as we know, divergence of a curl is always 0, therefore it is 0. And for the steady current, del dot j is also 0. But for the non-steady current, del dot j is not 0. This shows that the Ampere's law is bound to fail for the non-steady current. Maxwell modification of the Ampere's law. Now, first going to the modification, we will try to find the continuity equation, since it is one of the basic fundamental for the modification of Ampere's law. What we know, the charge in volume Q is equal to integration rho d tau. Now current flowing through the boundary surface is I dq by dt. Now Q, what we have, integration over the volume d tau. That means d by dt of integration over volume d tau rho d tau. Now, this is nothing but integration over surface current density J dA. Now, applying the fundamental theorem of divergence on the right hand side, we will have integration over surface J dot dA is nothing but integration over volume d tau del dot J. And this rho is a function of position as well as the function of time. So the time derivative became the partial derivative with respect to time when it moved inside the integration. That means partial derivative with respect to time of rho d tau is equal to minus of del dot J d tau. Now if we cut volume integration on the both the side, we will have partial derivative with respect to time of rho is equal to minus del dot J. This is the continuity equation. Now, second, correction in Ampere's law. Ampere's law. Now, Maxwell continuity equation which we have derived, del dot J is equal to minus of rho d partial derivative of rho with respect to time. By Gauss law, rho is nothing but epsilon naught del dot E. If we replace rho with epsilon naught del dot E, therefore del dot J is equal to minus deba by deba T of epsilon naught del dot E. If we take del dot outside, then minus of del dot bracket epsilon naught deba E by deba T. This minus sign, if we take this to the left hand side, del dot J is equal plus epsilon naught deba by deba T E is equal to 0. Now this is what we have current density, and this is what we have displacement current density. Maxwell defined as a displacement current density JD. Therefore, del dot J plus JD is equal to 0. JD is equal to epsilon naught deba E by deba T. Now, Maxwell put this displacement current in the Ampere's equation, then del cross B is equal to mu naught J plus JD. JD is nothing but epsilon naught deba E by deba T. And this shows that changing electric field produce the magnetic field. This is the one of the main conclusion. The effect of the magnetostatic due to this addition or Maxwell correction. In magnetostatic, deba by deba T or dE by dt is equal to 0 since the change in a steady electric field is 0 due to the constant electric field. Therefore, the modification does not change any conclusion of magnetostatic. So, we have still del cross B is equal to mu naught J of amperes when we are working on the magnetostatic. Maxwell equation what we get finally. Del dot is equal to rho by epsilon naught as we know as Gauss law. Del cross is equal to minus deba by deba T of B, Faraday laws. Del dot B is equal to 0 and del cross B is equal to mu naught J plus epsilon naught deba E by deba T. Ampere's law with the correction of Maxwell. The integral form is given below. Next topic is the magnetic charge. In this free space, there is no charge exists. Therefore, rho and J vanish. And therefore, the Maxwell equation reduced to del dot E equal to 0, del dot B equal to 0, del cross E is equal to minus deba B by deba T, del cross B is equal to mu naught epsilon naught deba E by deba T. If we replace E by B in first pair, there will be no changes. And B by mu naught epsilon naught in the second changes, vice versa. There is some corresponding quantity missing in del dot B and del dot E. That means if we replace E by B, it will be not making any change. But if we replace B by epsilon naught E, there is something missing. And that we had, if suppose we had like this, that L dot E is electric field, electric charge density rho E divided by epsilon naught. Similar way, if we had del dot B is equal to mu naught rho m, where rho m is the density of the magnetic charge. Same way, del cross E is equal to minus of mu naught Jm, where Jm is the current density of magnetic field minus of delta B by delta T, and mu naught J, del cross B is equal to mu naught Je plus epsilon naught delta E by delta T, where Je is the current density of electric field. Then these will get matched. These two equations will be matched with each other. That means Maxwell is suggesting to have a magnetic charge as similar as the electric charge existence. But by the experiment, we always know that rho m is equal to 0. Mathematically, he was right. But practically, we don't have any magnetic charge. Therefore, rho m is 0 everywhere, make the Jm to vanish, and the magnetic field is not symmetrical with the electric field. By the experiment, we don't have magnetic monopole, and that makes the magnetic charge is not present in the universe. And this makes the failure of the Maxwell conclusion. Now, Maxwell equation in material. As we have learned, the electrical polarization P produces the bound charge density, that is rho B is equal to minus of del dot P. Similar way, we have magnetic polarization result in a bound current, that is Jb is equal to del cross M. Now consider a small element of polarized material. Polarization result in a bound surface density minus of sigma b at one end and the plus of sigma b at the another end. Any change in electrical polarization involves the current flow, charge to flow, and that result into the current. Current in terms of the change in the surface charge density is given as dIp, current due to the polarization, and that is equal to current due to the charge polarization dt. Now here we have a surface charge density sigma b divided by dt into A. Now sigma b, we know that it is P n cap, vector P n cap. Now by definition of the current density, dIp is equal to jb n cap dA. Now if we equate these two equations, we get the result as Jp is equal to delta by delta T of polarization T. The polarization current density Jb is not related with the bound current density Jb. Don't get confused. Jp is something different and Jb is something different. Jp is the current density due to the polarization, whereas Jb is the current density due to the bound currents. And this bound current is due to the magnetization of the material. Now it involves spinning and orbiting, which polarization. So del dot Jp is equal to del dot delta by delta T of P, delta by delta T of P, del dot P, that is nothing but sigma B, that is minus of sigma B. Now above equation shows that the polarization of current density follows the continuity equation. Therefore, current density has a three terms now. First term, free current density. Second term, bound current density. And the third term, polarization current density. Now, we know bound current density is nothing but del cross M. Polarization current density, as we have found, delta P by delta T. The total charge density has, the total charge density has only two terms: free charge density and the bound charge density. Free charge density we know del dot P, as we know that if we replace rho by epsilon naught del dot E, we will get del dot D is equal to rho F. Maxwell correction and Ampere's law. What we have, del cross B is equal to mu naught J. In place of J, if we write JF del cross M, delta P by delta T plus mu naught epsilon naught delta E by delta T. Now, if we take this del cross M on the left hand side and if we add these two terms, we will get this is nothing but H, auxiliary field H, and this is nothing but D, electrical displacement field D. Maxwell equation in material medium in terms of free charge and current, then it will result into del dot D is equal to rho F. Del cross E is equal to minus dB by dt. Del dot B is equal to 0. Del dot J H equal to JF plus delta by delta T of D. And similar way, these are the integral form of Maxwell. Boundary condition. In general, the field, electric field, magnetic field this electrical displacement D, or auxiliary field H, will be continuous at the boundary between the two different medium or at the surface that carries the charge density sigma or current density K. The boundary condition describe how the normal component, that is perpendicular component, and the parallel component of these fields works going from one medium to another medium. Let's suppose for electrical displacement, the boundary condition for the electrical displacement. The Maxwell equation says that del dot D is equal to rho F. And the integral form we know, integration over closed area D dot n cap is equal to QF. Now consider a tiny Gaussian pillow box with each of side flat and parallel to the boundary on each side, and it is very close. Therefore, the integration over a closed area is equal to, depends upon the two terms d1 and d2, d1 n cap plus d2 n cap. Now what you know, and you can see from the figure that n cap 1 and n cap 2 are opposite to each other. Therefore, n cap 1 is equal to minus of n cap 2. If we put this in the equation, we will get d1 n cap 1 minus d2 n cap 1 is equal to qf. Now qf is free charge, which is nothing but integration over area rho f, sigma f dA. Now both sides we have surface integration. If we cut it down, the surface integration, we will have d1 n1 cap minus d2 n2 cap is equal to sigma f. That means d1 perpendicular minus d2 perpendicular is equal to sigma f. Boundary condition for magnetic field. Now, magnetic field we know del dot B equal to 0. That means integration over closed area D dot n cap dA equal to 0. That means if we take this equation, B dot N1 cap plus B dot N2 cap equal to 0. Again, we know N1 cap and N2 cap are exactly opposite to each other. Therefore, they are minus signs. We kept it, and that result into B1 perpendicular minus B2 perpendicular equal to 0. Boundary condition for electric field. From Maxwell equation third, we know del cross E is equal to minus of d by dt of B. Now, if we take both the side surface integration and apply the Stokes theorem on the left hand side, then we will have this equal to integration over closed line E dot dl, and this is as the partial derivative come out of integration, it becomes full derivative minus of d by dt of integration over the surface B dot dl, and this is nothing but the flux. Now consider a tiny Amperian loop at the boundary between the two surfaces. Now, the side of parallel to the boundaries have a length L, and the length perpendicular to the boundaries are very small and reduced to 0 in the limit cases. As a result, there is no contribution due to these two sides that are normal to the boundaries. Hence, integration over closed path E dot dl equal to E1 L n cap 1 E2 L n cap 2. As you know, n cap 1 is equal to minus of n cap 2. We will keep it down, and this is equal to by minus of d by dt of integration B dot dA, where we know that integration over the surface B dot dA is nothing but Im, and in the limit as the width of the loop goes to 0, the flux vanish. Therefore, we will have E1 parallel is equal to E1 parallel minus E2 parallel equal to 0. The boundary condition of auxiliary field H. Del cross H is equal to JF plus deba by deba T of B. Now del cross H, if we apply both the side the surface integration, and using the Stokes theorem on the left hand side, we will have integration over closed path H dot dl is equal to integration over the area JF integration over the area dA, and this JF is nothing but free current IF, which is equal to, since it is a surface current, KF cross n cap dot L. Once again, by referring the tiny impedance loop shown below and neglecting if contribution to the normal sides to the boundary condition, we get minus of integration of surface B dot dA is equal to 0. Therefore, what result? Integration over closed path HDL is equal to KF n cap L. Now, if we write this H1 LN1 minus H2 LN1 is equal to KF and cap L. LL could cancel. We will finally resulted as H1 parallel minus H2 parallel is equal to KF cross N cap. In case of linear medium, the general boundary condition for electrodynamics is D1 perpendicular minus D2 perpendicular is equal to rho f. E1 parallel minus E2 parallel is equal to 0. B1 perpendicular minus B2 perpendicular is equal to 0. And H1 parallel minus H2 parallel is equal to KF and cap. In case of no free charges or free current, the equation reduced to the 0. And this is our bibliography for above material.